we're going to do a video here on graphing polar equations. And before we really start, we should make sure we know a couple things, background things. For example, one of the things we need to know is graphing polar coordinates. So let's say we had, that's not what I wanted to do. Let's say we had two polar coordinates. Let's say we had 2 comma pi over 3, and we have negative 3 comma 4 pi over 3. I don't know. And actually, that's not going to be a good. Yeah, that's fine. Let's change this to 5 pi over 3. Okay, so we're going to graph these two polar coordinates, and we're going to graph the first one here in red. And what you need to remember here is that this is in the form of r theta, where r is the distance that this point is away from the midpoint here, which is called the pole. And at whatever angle off of the polar axis. And so that the polar axis is this axis here, and we're going to draw, and we're going to go that way with our angle. And so, if we want to graph where 2 comma pi over 3 is, all we need to do is go and look towards pi over 3. You can imagine we're standing on the pole and looking towards pi over 3, and since it's a positive 2r, we're just going to go 2 out from the pole. And these concentric circles around the pole are just distances. They're the circles of which every point along that circle is that given distance away from the pole, in this case 2. So that right there, that red dot, is how we would graph the coordinate 2 comma pi over 3. If we wanted to graph negative 3 comma 5 pi over 4, we do this the same way. We stand, like we can imagine we're standing at the pole and we're looking towards 5 pi over 3, so we're looking in this direction here. Now, instead of going 3 towards that direction, if it was positive 3, that's what we'd do. We would have a point right here, but it's not, wait, sorry, not right there, it would have been right here. I can't count. It's not positive 3, it's negative 3, so instead of going 3 that direction, we're going to go 3 back from there. So 1, 2, 3. This is where our blue point should be. And so understanding this negative r value is really, really very important. The other thing that's that we're going to need as like kind of a requisite for the way that I'm going to show you this is recalling how to graph a trigonometric function. So an example of a trigonometric function, just say y equals sine of x. That's a pretty simple one. If we have this and we know that our amplitude is 1, that's the value in front of the sine. It's just 1 in this case. The period is 2 pi, because usually period is 2 pi over omega. 2 pi if the fundamental period of the trig function we're working with is 2 pi, and it's sine in this case, so it is 2 pi. Omega being the coefficient of this input x, which is 1 in this case. So 2 pi over 1, the period for this is 2. There's no vertical shift or phase shift for this because there's no value that's getting added to the sine of x. And there's nothing that's being subtracted from the x itself, or added or subtracted from the x itself for a phase shift. So we don't have to worry about that. What we do need to do is figure out where the crucial points are going to go, and to do that, we find the tick marks along the x-axis, and we take the period, which is 2 pi, and divide it by 4. That's going to give us pi over 2. This value is how far apart each tick mark should be from the previous one. And we're going to start at 0, which means the next one should be at pi over 2. The next one should be at pi. The next one should be at 3 pi over 2. The next one should be at 2 pi. I just added pi over 2 from here to here, from here to here, from here to here, from here to here, from here to here. So then the last step is to, that got really crooked. The last step would be to just graph this. Well, it's also real crooked, but I'm doing my best. We're gonna go 1 up. You're going to go, what is going on? We're gonna go 1 up, and we're gonna go 1 down. That's the amplitude. That's 1. That's negative 1 is 0. We're going to go over to pi over 2, over to pi, over to 3 pi over 2, and over to 2 pi. And then we're just going to know that this is positive sign. Positive sign starts at the midline. It goes up to the top, the maximum, the positive amplitude. Down, goes back down there. And if we're going to connect these with a smooth curve to graph y equals sine of x, you know it's going to do something like this. And it's going to keep going in either direction. And so those two concepts, graphing polar coordinates and graphing trig functions, are super crucial to a really good understanding of how to graph the polar equations. So the first kind of polar equation we're going to look at here is something called Limaçon. This little letter is pronounced like as an S kind of, so Limaçon. And there are three different types of Limaçons. There's a Cardioid that looks like a peach shape, kind of looks like this. There's a Limaçon with a dimple that's similar, but instead of coming to like a little peak there, it just kind of, it does kind of like a little curve in, kind of looks like a bean. This is a really poor drawing, but it looks something like that. And then there's a Limaçon, which looks something like this. Has like a little loop in it. Sorry, Limaçon with an inner loop has a little loop in it. And we'll see an example of each of these in a minute here. This information here it can be really good to know if you are given an equation, a polar equation that looks like something in here, and you compare the values of a and b, and you don't take into consideration these negative signs. You just think of a and b as values themselves, not positive or negative. If you compare them, you will be able to know what thing you're graphing. I don't know what just happened there. What happened to my stuff? I don't know. Anyway, so let's look at the first one. We're going to graph this right here. And we know if you go back and look at the criteria for this, I know right away this is a cardioid, and I said so on the slide anyway. So this is a cardioid, and the way we're going to go about doing this, well, I'll show you two ways actually. The first way would be to make a table of values for theta and r. And we do theta and r, not r theta, because theta really is the input here. Like this value, this is the input. And then we evaluate the stuff on the right side, and we get the output, which is r. This is the output. And so when we want to plot points, when we want to pick points and evaluate and get a bunch of points that we're going to graph, we plug the input in, and we list the input first and the output second. So we are going to specifically choose 4 different inputs that are very important. They are the cardinal values, the cardinal angles. So theta being an angle, we're going to specifically evaluate for the 4 cardinal angles, which are 0, pi over 2, pi, and 3 pi over 2. Again, 0, 0, pi over 2, pi, 3 pi over 2. And if we plug these values into 4 plus 4 sine theta, the sine of 0 is 0. So 4 times 0 is 0. 4 plus 0 is just, this is going to be 4. If you plug pi over 2 in, you will get that the sine of pi over 2 is 1. It'll be 4 plus 4, which is 8. Okay, let's do this one. Just write it out here. If we want to know what r is when when theta is pi, well, we know that 4 is 4 plus 4 is sine of theta is sine of 180 degrees. That's 0. So that's going to be 4 plus 0, 4. That's how we're doing this math. 3 pi over 2, sine of 3 pi over 2 is negative 1, so 4 minus 4, this would be 0. And if you get these 4 points and you know exactly what you're trying to graph, you know that this is a cardioid, it's possible to do a pretty accurate sketch of that cardioid. I will demonstrate that now. So these points, we're just going to plot them. So for the first point, we're looking at 0, and we're going 4 in that direction. Okay, so we have a point right here. The second point is pi over 2. So we're looking at pi over 2, and we're going 8 in that direction. That's, I believe 8 is all the way at the top. I think. 1, 2, 3, 4, 5. Yeah, I think so. And then pi, we're looking at pi, that's over here, and we're going to go 4 in that direction, because it's positive. 1, 2, 3, 4. Okay, so we're right there. And then we have 3 pi over 2 looking here, but not going anywhere, seeing 0. So we have that point there. And since I know this is a cardioid, the only possible way that this could look is something like this. Starts there. We actually start drawing it here. Then it's kind of gradually circles out until it gets to that 8 there, and does the same thing on the other side. And then it kind of loops back in here, and you get that. And that is what this is going to look like, and we'll verify that in a minute. But that's totally a legit way to do this, is picking those 4 cardinal points, knowing that it's a cardioid, and given the points how they laid out, it could only ever look like this. You could go and check this on Desmos if you're curious, but this is exactly correct. I mean, it's a sketch, so it's not exact, but it's correct. The other way to do this, the other more detailed way to do this, would be to look at a comparison between a rectangular version of this cardioid, of this equation, and then transfer that rectangular graph to a polar graph. And I think if you can see the relationship between those two things, that's very important. That's a really crucial thing to understand when it comes to polar coordinates. Okay, so whereas in this polar equation that's given to us, our input is theta and our output is y. What we're going to do is instead graph y equals 4 plus 4 times the sine of x, where x is my input and y is my output. And when we do this, we can graph this in a rectangular fashion, and we're going to extract some information from it. So the crucial pieces of information are this, and the number in front of that x, which is 1. And so from that information, we can get the amplitude of this function, of this trig function here. We can get the period, which is capital T. We can get the phase shift, and we can get the vertical shift. These are all going to be really important, and not the phase shift because there isn't one. But the amplitude of this is from this number here, which is 4. The period is 2 pi, and then we would divide that 2 pi by the coefficient from the x, which is 1, so it's just 2 pi over 1. The phase shift, if there was something out here that the x was being added or subtracted from the x, we would have a phase shift, but we don't, so there isn't one. The vertical shift is this number here. If it's positive, it's up. If it's negative, it's down. This is positive. So the vertical shift is 4 up. Okay, now the last thing we need to do is figure out where the tick marks along the x-axis should go. So for tick marks, we are going to take the period, which is 2 pi, and divide it by 4. For that we get pi over 2. So our tick marks are pi over 2 away from each other, and the first one, because there is no phase shift, is 0. Then we're going to add pi over 2 to get pi over 2. We're going to add pi over 2 to pi over 2 to get just pi. If we add pi over 2 again, we'll get 3 pi over 2. If we add pi over 2 again, we'll get 2 pi. So that's how we're going to label the x-axis. So let's just draw a quick axis right here, and then let's see, we've got a vertical shift of 4 up. Then the amplitude is going to go 4 up and 4 down from there. So we're going to be going up to 8 and down to 0. And then along the x-axis we will have pi over 2, pi, 3 pi over 2, and 2 pi. And the last thing is we will graph this. So we're going to graph it along the midline. Like this is sine, it has a midline. I don't know what just happened there. See if I can go back to this somehow. Sorry, technical difficulties. Okay, so we're going to go, sine it starts right here. The next point's high because it's positive sine. The next point's middle. Next point's down. Next point's back to the middle. And then finally, this graph is going to look like this. It's curved more than I have indicated here. It's hard on this screen. So that's the graph of 4 plus 4 sine of x. Now how does this graph help us when it comes to graphing the original equation, which is r equals 4 plus 4 sine of theta. This is how. So whereas we have essentially our y and x value here, we could pretend that this is like, these are r values along the y-axis, and then these are theta values. Obviously they are theta values, they're angles along the x-axis, or the horizontal axis. And so if we start pulling points off of this, we can get a picture for we can get an idea what it's going to look like on the polar coordinates. So the first point that we see, let me do this in green, is this point right here, which is 0 and theta and 4 and the radius. So we're looking at 0 and going 4. 1, 2, 3, 4. There's a point right there. Okay, now the next point, clearly the next main point we see is pi over 2, 8. So if we're looking at pi over 2, we're going to go to 8. And that point is right there. Now, why did we go through the trouble of drawing this if we already had 0, 4, and pi over 2, 8 from this table? Well, the reason for that is we don't exactly know, like, unless we know exactly what the cardioid looks like, we don't know how these two dots are connected. And the way that we can figure that out is by looking at these smaller points here. So if you, not the smaller, uh-oh, how do you undo that? I don't know how to undo that. Well, let me just draw the curve back in. Did this. If we look at these points, so we've got, like, right after this point, there's the value for r is from the 0 x-axis all the way up. It's just a little bit bigger than 4, and our angle is really small. It's like pi over 2. It's like, maybe let's say it's pi over 12. So like here's pi over 12, and our angle is greater than 4, but just barely. So at pi over 12 we should be greater than 4, but like just barely. So maybe like in this area. Okay. And then if we go a little farther than that, maybe let's say that this here is pi over 3. Okay, let's say that's pi over 3. That looks like it's about, I don't know, like 7 something. And we can get the exact value for this if we had, if we evaluate. All you have to do is plug in, like, so if you plug pi over 3 into this equation, you would get 4 plus 4 times the sine of pi over 3. The sine of pi over 3 is root 3 over 2. So that'd be 4 plus 4 times root 3 over 2. So 4 plus 2 root 3. I don't know what root 3 is off the top of my head. It's like 1.7 something. 2 times 1.7 something is like 3-ish. So 4 times 4 plus 3. We would have, like, at pi over 3 we should be somewhere around 7. A little bit more than that actually. So at pi over 3 we should be somewhere around 7. And you can get a better sense now that we have these other points of what this curve should do. You can see that it's going to kind of go out like this and get wider and wider and wider until it is able to pick up those points and do that. Okay, now at this point where we're just right here, we have to kind of go back down. We have to go back down the slope here. So we're going to have positive radii, but they're getting smaller until they get back to 4 when we're at pi. So at pi, our radius is 4. 1, 2, 3, 4. We're going to end up having to go through that point, and our radius is going to start off really high. Right here at this value, it's really high, and then right here it's closer to 4, and like in the middle, it's, I don't know where that is. And so we need to, like, gradually decrease until we get back down to that value. Okay, now we're right here. And as we are moving this way, as we're reading left to right on this graph, we are rotating around this direction on the polar graph. And so we need to keep going. And at just past pi, we have a positive radius, but it's less than 4, and it's decreasing all the way until we're going to get to 3 pi over 2 and 0. So we're going to end up back at this point. But there's a gradual decrease in that radius until it gets to that point. And then if you are here, you'll see that from there we have that 0 radius, and then it's going to very gradually increase until it gets back to our original point, which is right there. And so that's a little bit more of an accurate graph where you can see how these curves over here are reflected by these curves over here. It's as if we have warped this sinusoidal curve around like some midpoint and gotten this weird shape here, which is called a cardioid. Alright, so this next one here is a little bit different. This is not a cardioid now. This is going to be a Limaçon with a dimple. And if we didn't know that, we just graph it, and from the graph we'd be able to tell what it was. But this is a Limaçon with a dimple, and it's done very similarly, just the numbers look a little different. So we can, we'll just do this the full way that we did the last one instead of doing the table of 4 values, which you can of course do. The table of values. Again, you're going to pick those cardinal angles, which were 0, pi over 2, pi, and 3 pi over 2. And when you plug those in, if you plug in 0 for cosine, you get 1, so 4 minus 2, that'd be 2. When you plug in pi over 2 for cosine, you get 0, so that'd just be 4. When you plug in pi for cosine, you get negative 1, so it'd be 4 minus 2 times negative 1, so it'd be 4 pi, this would be 6. And then 3 pi over 2 would be 0 for cosine, so 4 minus 0 is just 4. So those are the points you would plot, and then you could figure it out if you knew what a Limaçon with a dimple looked like, which we kind of don't, as if you hadn't seen anything like this before. You wouldn't exactly know what this looked like. So let's look at more detail by graphing. Instead of r equals 4 minus 2 cosine of theta first, let's look at y equals 4 minus 2 times the cosine of x. And just like we did the last one, we're going to want to get from this the amplitude, the period, and the vertical shift. There's no phase shift, so just forget about it. And the amplitude is just going to be 2. For the same reason 4 was the amplitude of the previous one. The period is 2 pi. For the same reason 2 pi was the period of the previous one. That this number in front of the x is a 1. So it's 2 pi over that number. So it's just 2 pi. The vertical shift is 4 up. For the same reason it was 4 up. In the previous problem, this is a vertical shift and it's positive, so we shift 4 up. Okay, now we also need the tick marks. And the tick marks are found again the same way. We take the period 2 pi and divide it by 4. We get pi over 2. Each of these spaces along the x-axis are going to be pi over 2 away from the previous one. And we're starting at 0. So if we take 0 and we add pi over 2, we just get pi over 2. If you take pi over 2 and you add pi over 2, you get pi. You keep going until we get to 2 pi. The reason we want to get to 2 pi is because if you look at this polar graph, it goes from 0 and then goes all the way around to 2 pi. So if we have enough information on the rectangular graph to get to 2 pi, then we will have enough information for the polar graph. Let me just erase some of these things because, first of all, this is not at all a straight line, and let's get rid of this circle because I don't need it. Okay, so let's try to fix this and do actually a good job for once. It's alright. Okay, so what we need to do is notice that we're going to shift up 4. So let's say that's 4. And then from there, we're going to go 2 up and 2 down, which is the amplitude. So we're going to be up here at 6 and then down here at 2. And the midline is at the 4. Okay. Let's try the tick marks along the x-axis are at pi over 2, pi, 3 pi over 2, and 2 pi. And then we're going to just draw on our curves. Now notice we have negative cosine here. So negative cosine starts at the bottom, meaning it's going to start right here at 0, 2. Then we're going to go at the next tick mark, it goes up to the midline. At the next tick mark, it's going to be up at the highest point, then back at the midline, and then back at the lowest point. And if we connected these dots with a smooth curve, we would find that the graph of cosine here, the graph of 4 minus 2 cosine x, looks something like this. And again, this is going to keep going. It's sinusoidal curves, trig functions in general are periodic. They're cyclical. They keep going forever, unless we restrict the domain, which we haven't done here. Okay, now let's start transferring those points over. So the points are the first point that we see. Actually, let's use I don't know, yellow. This point here is 0, 2. So if we're looking at 0, we're going to go 2. So we have a point right here. You see this yellow? Yeah, it actually shows up pretty good. Okay, so there's our point 0, 2. And then we have another point here at pi over 2, 4. So we're looking at pi over 2 and going 4, 1, 2, 3, 4. Now what happens between the 2 and the 4? What happens between those 2 points we just drew? Well, to do that, we kind of have to look at points in between these points right here. And so you can see, like, after it leaves 2, we're reading this direction. We're going from 0 out to 2 pi. And as we leave 0, we see that the radius is increasing. Like, this value here is increasing until it gets to pi over 2. And if we transfer that, if we translate that over here, that means as it's leaving this point, it's getting larger and 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 larger until it gets to 4 at pi over 2. Okay, then we have, and it also kind of gradually, like if you actually notice, it gradually gets bigger. So it's actually gonna kind of do one of these, and we'll clean this up later. But after we're at pi over 2 and 4, we'll see that we're gonna end up going from pi to 6. So here's pi, and we go 6 in that direction. 1, 2, 3, 4, 5, 6. This is pi 6, and again we're going to we're actually kind of drastically taking off from the 4 and going towards 6. Like, it's actually going faster away from 4 here than it is getting closer to 6 here. So you could kind of think of this as like doing this. Well, that's actually not a good example. It's kind of doing this. Let me erase that other line. It's not easy to draw these. If you make tons of mistakes while drawing these, that's fine. You just erase it and redo it. I'm actually going to redo that line too because I don't really like it. I'm just going to do something more like this. Okay. Alright, so we're there. That point, this point here, was this point here. Okay. Now, if we look at where it goes after that, it does the same thing on the other side. Like, as it came in from that way, it's going to leave the same way as we go back towards 3 pi over 2. And the value at 3 pi over 2 should be 4. So 3 pi over 2, 3 pi over 2, 4. So 3 pi over 2 looking this way, going to 4, we should be out here for our next point. And we're going to gradually leave this point and then swoop in. Maybe go a little wider. Go a little wider than that, swoop in and get to that 4 there. So let me try to erase the screw up. Oh, that didn't work out so hot. Try it again. So it's gradually leaving. Yeah, something like that. And then, so that point there, 3 pi over 2 was this point here. Okay, now look what else is happening. So we're going to leave that 3 pi over 2 and head towards 2 pi. So we're looking at this section now, which should be the same as the first section we drew. So whatever we had on top, this kind of area, let me circle this in blue. Like, this area here should be mirrored over here, and that's what we're going to do. All of these graphs, all of these polar graphs are going to be symmetrical. Limaçons are symmetrical. So we have something similar over here. Let's see if we can draw this with any kind of accuracy whatsoever. That's not very good. It does something like this here. And if you wanted to get more detail about what was happening to this, you would just plug in some more points and get like real good values and plot them and then connect the dots in a little bit more accurate way. But this looks like kind of as if it's a circle that got punched in on the side. It has this little dimple in it, and that's what the graph of this should look like. Alright, the next one we're going to do is the last kind of Limaçon. That's a Limaçon with an inner loop. Okay, this one's going to be a little bit different than the previous two. It's still a Limaçon, but this one's going to look a little different. And you'll notice here the relationship between A and B is that A is less than B. And whenever you have that A is less than B, you're going to end up with this thing, this inner loop looking thing. And so let's start. Actually, let's do these 4 values again. These cardinal points, or the cardinal angles, where you're going to get the 0 pi over 2 pi and 3 pi over 2 angles. Just to show you, just to illustrate how you don't always know what this is going to look like unless you're very familiar with what a Limaçon with an inner loop should do, because there's not going to be enough information here by picking these 4 points to really do any kind of accurate graph, unless you're like super comfortable with what this is supposed to do. So if you plug in, ooh, come on, it went away, come back. Oh no. If you plug in 0, cosine of 0 is 1, so 2 plus 4, because 4 times 1, so 2 plus 4 is going to be 6. If you plug in pi over 2, the cosine of pi over 2 is 0, so you're just going to have 2. If you plug in pi, the cosine of pi is negative 1, so it's going to be 2 minus 4, so you're going to be at negative 2. And then you have 3 pi over 2, which is just going to be at 2. And so if you graph these, something kind of interesting happens. So we're going to look, the first one, if we're looking at 0, we're going to go to 6, which I believe is right here. I can't count, yeah, that's the 6th ring out, so that's 6. Okay, then pi over 2 and 2, so it's right there. Looking pi over 2, going positive 2. Now if we're looking at pi, we're going to go negative 2, which this is interesting. I don't know how to get to that point. And then 3 pi over 2, looking 3 pi over 2 and going 2 in that direction. So we have a point right here. And like, to me, there's no clear way to connect these dots. Like, what are you supposed to do? Does it look like that? Like, does it do something like that? I mean, obviously I'm not doing a very good job on that, but it does a weird thing that we don't have enough information by simply applying those few points. And so to really get a better picture, again, what we're going to do is instead graph y equals 2 plus 4 times the cosine of x on a rectangular plane, rectangular coordinate system, and then transfer the points over. We have some more detail that way. So, and this is really, honestly, this version of Limaçon with inner loop is the most, besides maybe at rows, is like the most useful. It's the most useful to do this method to get a better picture. So again, amplitude, we want the period, and we want to look at the vertical shift. There's not going to be a phase shift. So the amplitude is going to be 4. The period is just going to be 2 pi because there's nothing in front of that x. Well, there is. It's 1. It's 1 in front of the x, and then the vertical shift is just 2, and it's positive, so it's up. We also need tick marks. I'm trying to make this come up. Tick marks are going to be, again, 2 pi over 4, so pi over 2. So the tick marks are your standard tick marks for a normal trig function that's not been stretched in any way. 3 pi over 2 and 2 pi. So let's graph this real quick. So our vertical shift, we shifted 2 up. So let's say that's 2. Now our amplitude is going to be 4 up from here and 4 down from here. So 4 up is going to end up here at 6, while 4 down is going to end up down here at negative 2. And our midline is at that 2 where it got shifted up to. And then our tick marks, horizontal tick marks, we got one at pi over 2, one at pi, one at 3 pi over 2, and then one at 2 pi. And then it's cosine. So cosine, it's positive cosine. So positive cosine starts high up. It goes down to the midline. The next tick mark's down at 0, or not 0, but the lowest point. Next tick mark's back at the midline. And then last one is up high. And if we connect these dots, let's use green for this. It's going to look something like this. It's more curved here. Okay. And now you'll notice like we dipped below the x-axis here for the first time, and that's actually what causes this inner loop thing. And very, very, very crucially to this, we just found these points right here. We don't know the exact angle value of those points, but it clearly crosses the x-axis. It crosses. Remember when we're plotting this theta versus r here, it crosses the where r is 0, so it's going to end up going through the pole. Anytime r is 0, whatever curve or line or whatever you're drawing is going to go through the pole. Because it doesn't matter what angle you're looking, if you're going no distance in that direction, you're at the pole. So anyway, let's start transferring points over here. The first one we have is 0, 6, so we're going to be looking 0 and going 6, so we have this point right here. Okay, now as we're moving this way, you'll see that the radius is still positive, but it's decreasing. It's decreasing from 6 to 2, and it is 2 at pi over 2. So if we're going to look pi over 2 and go 2, we're going to be right here. So if we draw what we just said, the radius is going to be, it's positive, but it's decreasing. So as we're rotating this way, our line is, or like where our line is going to be closer and get closer and closer to that pi over 2 value. So it's going to kind of do something like this here. Okay. So it's a little too fat here. I'd say it probably needs to be more like that. But you can. It's really hard to get this perfect again unless you pick like exact points. Which we can do. Like pi over 3 would be a really easy one to do here because cosine of pi over 3 is a half, and if you plug that in, you'd have 4 times a half is 2. The point should be at pi over 3. We should be right there at 4, so we should really be hitting that point. Anyway, that's besides the point. If we are graphing this way, we're now looking at this point right here. So we just stopped at pi over 2, and we need to move past this. So we're going to do that like we normally would. Like notice after pi over 2, right immediately after it, it's still a positive radius, but we're rotating from pi over 2 towards pi, and we have a positive radius, but it's going to go through 0 at some point in between pi over 2 and pi. So it's going to do something like this here. So it's going to go through there, and it's going to cross. It's going through the pole at some angle there. We don't know the exact angle because this whole section is kind of imprecise, but it's between pi over 2 and pi. And when we get to pi, we have a value of -2. So if we're looking at pi, we're going to go -2. So we should have another point right here. And now how we get from where we are at the pole to that point is kind of really important. It's because now we're dealing with these negative radii. And so this section here of the curve, we have a radius that starts at 0 and then is very small but negative. It's a very low negative number, like very close to 0. The magnitude of it's small. And then it gets bigger, it becomes like a larger negative number until it gets to -2. And if we're drawing, like you can imagine, let's say that was the angle at which we got an intercept at the x-axis. We have a radius 0. Anything from here over, we're going to be drawing negative radii values, meaning we're going to be drawing on this side over here. And so this is going to do a negative little kind of spiral out until it hits that value there of pi, the pi -2 point. Now, by now you should realize that all this stuff is symmetrical. Like everything here is symmetrical. If you divided this cosine curve in half, you would see that this side and this side like are reflections across that dotted line. So we can just reflect what we have drawn here, or we can keep going and look at like what's happening. It's going to have a negative radius of 2, and then it's going to get smaller and smaller, closer back to 0 as it approaches some angle in between pi and 3 pi over 2. So we're going to be rotating this way, drawing negative values until we get back to 0 at some point. So it's just going to do one of these. Again, it's going to go back through that pole. It's going to go back through, at that point right there, it's back through the 0. Alright, then we have this point here at 3 pi over 2 and 2. which should be, if we're looking 3 pi over 2 going 2, we're right here. And we're going to kind of do just like we did on the other side. It has a now we're looking kind of right, maybe right here, going this direction still. And we have positive values for radius, so we're going to be drawing where we should expect to draw with positive values, which should be out here. Okay, so we go back through that point, and now we're right there. And the last thing to do is have an increasing radius. It's increasing fairly quickly until it gets to 2 pi. So we know from before that if we put in a pi over 3 reference angle, we're going to get 4 out. So we want to go through this point right here. And so when we draw the line, we're going to use that as a guide, kind of shoot out to that point, and then gradually come back. It's very hard to draw this. Obviously this is smooth, it doesn't have these bumpies in it here, but that right there is your Limaçon with an inner loop. And if you see, like, this whole part we drew here, that's what is causing this inner loop. It's these negative radii values. And the next thing we're going to look at is a rose. And a rose has all kinds of negative values. But because it is like as much above the x-axis as it is below the x-axis, we have more loop-de-loop stuff kind of happening with the roses. So look at that here next. Okay, so this next one we're going to look at here are their roses. This is an entirely different looking graph. It's still a polar graph, but it's in a different sort of form. And the standard form we're going to see here is like r equals a cosine theta, or r equals a sine theta, where there's a multiplier to the theta, some n value. This should remind you of omega when we're dealing with rectangular, just standard trig functions that we're graphing. Now there's a couple of rules that are pretty useful for knowing for roses, and those really the main ones here. A is the length of the petal, so this a value is the length of how long a petal is, and if that's confusing to you, don't worry, it'll be very clear what a petal is once we start graphing this. The other thing here is primarily this. If n is even, then there are 2 n petals. So like, for example, let's say we had r equals 3 times the sine of 4 theta or something. Well, this n, is even. And so if we had, we would have on this rose, there would be 8 petals. Okay. Now if it was the opposite, let's say it was 4 times the sine of 3 theta or something. 3, this is odd, so there's only just 3 petals. Okay, 3 petals. This one would have been 8 petals. And that's really the most important stuff here. There's some shortcuts. There's ways to figure out exactly where the petals are going to go. Once you get a sense for drawing these, it's really, they're all kind of the same. But we're going to go through the same process we've been going through for this rose problem here. So let's take a look. Alright, we got r equals 4 times the cosine of 3 theta. So again, we are going to, instead, we're going to try a different input and output. We're going to do y equals 4 times the cosine of 3x. Okay, and now just like before, again, we're going to do amplitude. That's going to be 4. That's what's in front of the cosine. We want period. We're going to hold on to that for a second. There's no vertical shift because there's nothing added at the end over here. Okay, none. There's no phase shift. Phase shift is also sometimes just called phi. There's none of that either. So the period, remember, the fundamental period of cosine is 2 pi, and then we have to divide that by omega. I don't know how to get rid of it. Okay, so 2 pi over omega, where omega in this case is what's multiplying by the 3, which is, multiplying the x, which is that 3. So it's 2 pi over 3 is what the period of this thing is. Okay, now, last thing we need to look at here are those tick marks. And this is kind of really important because this is going to determine all kinds of things. And the tick marks are the period, 2 pi over 3 now, divided by 4, which is 2 pi over 12, which is pi over 6. So all of my tick marks are going to be pi over 6 away from each other. There's no phase shift, so the first tick mark's at 0. So we got 0, we add pi over 6, we get pi over 6, add pi over 6 to that, we get pi over 3, add pi over 6 to that, we get, that was 2 pi over, so this would, sorry, that was 2 pi over 6, so we get pi over 2, 3 pi over 6, that's 2. That is obviously a 2. I don't know what you're talking about. And then the next one, if we add 3 pi over 6, we add 1 more pi over 6, we get 2 pi over 3. We get 4 pi over 6, which is 2 pi over 3. So those are going to be my tick marks. Let's graph this. So here's your XY axis. And let's do some markings here. So 4 is the amplitude, so we're going to go 4 up and 4 down from the 0, because there's no vertical shift. And then our tick marks, again, are at pi over 6, pi over 3, pi over 2, and 2 pi over 3. And we have positive cosine, so positive cosine starts up high, goes down to the midline. Oops, I keep pushing this button on this pen, and I don't know what the button even does except for annoy me. So it goes from the top down to the midline, and then the next tick mark is down at the bottom, then back at the midline, then up top. And so this graph will look something like this. Okay, and it would keep going, and that it would keep going is going to be pretty crucial for this, and you'll see that in a minute. So we're going to go left to right this way, from left to right, and we're going to read the angle values, get the r values out. Remember, this is r versus theta, and then we're going to transfer them over to the polar coordinate system here. So 0, 4 is your first point. So you're looking 0 going 4, 1, 2, 3, 4. We have a point right here. Okay, the next point that we have here is pi over 6 and 0. So if we were looking at pi over 6, which is right here, we would be going 0. So that's weird. How do we go? Is it a straight line back? No, it's not. And we get that information from the graph. Like if we look at this distance here, this is the radius. This distance here is how far away we should be from the pole when we're at whatever the angle that is corresponding to this. And so you can see like halfway between 0 and pi over 6, we're still pretty close to 4. But then really quickly after that, it's going to go back to pi over 6. And so what this is going to look like when you draw it in is something like this. You're at that 4, and it's pretty close here, but then it goes quickly back. Okay, and polar functions are continuous, so we're going to just keep drawing in the direction we're kind of drawing. Like that's a good indication of like where you should be drawing your next like lines. But let's look in more detail at that. So right now we're at this point here. And now what we're going to do is continue this direction, and we're going to end up with this point at pi over 3, negative 4. So this one's, we're looking at pi over 3, and we're plotting negative 4, so we're going 4 back. We should have a point right here. Okay, and how do we get from where we were at the pole to that point? Well, you have to look that there is a negative radius. So as you're looking like these angles right here, we have a negative radius. And that not those angles right here. As you're looking at from pi over 6 to pi over 3, that's where we have we have negative angles at the other part too. But for now, we're only that far. We're not quite over there yet. So from pi over 6 to pi over 3, we have negative angles. So as we're looking over here, I just deleted that. As we are looking over here, we're going to be drawing in angles on the other side because we have negative radii. So that path that's going to follow is very similar to the previous path. Like we're going this way, and then we're going to come out. That wasn't very good. We're going to come out and curve in right there. Because those are all my negative radii there. Let me get rid of that little line right there. Alright, cool. So we're there, and that's at pi over 3. That point, that green point there is at pi over 3, negative 4. So now we're going to come back to this point, pi over 2, 0. So we're going to have to come back looking pi over 2 going 0. And the way that's going to connect is just to kind of come back the same way it's been going. Like these are all sort of symmetrical. Okay, the next point we see here clearly is 2 pi over 3 and 4. So if we're looking 2 pi over 3, we're going to go positive 4 in that direction. So 1, 2, 3. We should have a dot right here too. That should be green. Okay, and we are in the process as we were drawing this. We were going this way. Okay, and we're going to continue kind of drawing that way. We'd be coming like right up, getting to there, and then we're going to kind of go the same way and come back. And these petals that we're drawing here are all going to be roughly the same width. That width is very hard to determine without getting like a bunch of in-between points, which we're not going to do. But then we don't have more information here on the graph. Like we don't know what it does. I mean, we do know what it does because like we understand trig functions are cyclical. That's just going to come back and hit here at that next tick mark. Okay, which if you add up another pi over 6 to 2 pi over 3, you'll get, what will you get? That'll be 5 pi over 6. So at 5 pi over 6, we should be back to 0, which is what we had right here. That's that part we just drew. This part here was that part we just drew right there. Okay, and then if you kept going again, you'd end up right back here at pi. This would be pi. You add 1 pi over 6 to, you add 1 pi over 6 to 5 pi over 6, you get 6 pi over 6, which is pi. And the value there would be negative 4, so I'd be back at my original starting point right here. And so I'm going to have to connect that back like this. And that right there is a rose. And there are all sorts of tricks to this to figure out how far away each rose will be, where the maximums will be. So like how far is it from here to here? And notice that whatever that angle is, that's gonna be the same angle from there to there, and the same angle from there to there. The spacing is, it's not by coincidence that it's all the same. The other thing to notice here is that if we look back at this graph, these maximums, this one here, and this one here, correspond to, the maximums and minimums. So that first one corresponds to that first point we drew. The second one corresponds to that second point we drew. And the third one corresponds to the third point we drew. All the stuff in between is, is based on how this curve goes. If we kept drawing this out, if we kept going with this, you'd see that this point here was obviously back at this point here, because that's where we ended this. If we went here, you'd see this point here would end up back at this point here. If we went down here, we see this point ends up back at here. And like this would just keep drawing over itself, this rose. And so we don't do that. We just draw until it connects back to itself. So that's kind of a trick to look at how you know how much of this you're going to need to draw. It's like however many petals you have. So we had 3 petals. We're going to need these 3 maximums here to draw these 1, 2, 3 maximums here to draw this. I just drew all over my graph. It doesn't even look like anything real anymore. But yeah, I mean that's really all there is to roses. Sometimes you'll have much uglier looking numbers. So like especially if there's a 5. If there's a 5 right here, it gets right here. If there's a 5 right here, it gets pretty nasty because that's no longer a common angle that you can just easily plot on a standard polar coordinate system. But anyway, that's it. Now, the one last thing I wanted to show you real quick is a visualization of how what's happening when we go from this to this. Like there's a animation that I found online that I think is really helpful for this. So let's take a look at it, and I'll kind of walk you through it real quick. So here's a rectangular graph. It's y equals sine of 6x plus 2. Now we're taking the inverse. Essentially, we just reflect over the line y equals x, and then we warp that axis, that theta axis, kind of around a point to make it radial instead of linear. And if you think about it, here's some explanation for that. But when we have a standard rectangular equation, like a rectangular standard trig function, we have x and y, where x is the input and y is the output. When we have polar coordinates, we have theta as the input and r as the output. Notice the order. Like this is the first one, this is the second one, this is the first one, this is the second one. The input is first in x and y, and the input is second in the r theta. And so that's why this reflection over the line y equals x happens right away here. essentially what we're doing is swapping the input and output to get it in the order we're more familiar with. We want to be plugging in a theta and getting an r out. And then that warp there is how we kind of wraps it around that point. That's kind of how we get that radial circular kind of graph off of the rectangular graph. We did some of that in our head, like right over here, right? We were pulling off theta values and then getting r's instead of looking at r's and getting thetas, and that's sort of what this animation here represents. So I hope that was helpful to you. Please let me know, give me feedback. If you would like to see videos on other things, just make sure to put it in the YouTube comments, and like and subscribe, and make sure to hit that bell for notifications.